right, welcome to Building Jinky Programs. I'm Philip Forkner, professor at Pierce College, and we have also with us Jasper Newkirk, student in the computer science department at University of Washington. What's up?
What's up?
Okay, so today I think we're going to talk about recursive backtracking, and Jasper and I have already been chit-chatting about it a little bit, and we're going to work on this problem from the Code Step-by-Step website, which is a really great website if you want to do some practice. They have Python and Java and I think several languages where you can hop on and do practice problems. Anyway, we use it in our class. And so one of the problems that we're working on is something called escape maze or maze.java. And I think actually I should have prepared this beforehand. There's a Geeks for Geeks website where they do a rat in a maze, I think, problem. But there's several of them. There's like a knight's problem. There's the queen's problem. Anyway, I'm going to go ahead and get my screen share going here. And so this is the problem. And again, if you hop onto the Code Step-by-Step website and you got to search for it, maybe we'll put a link or something, but this is it. And so our job is to use recursive backtracking to find a solution out of this maze. So you can see it's kind of like there's these hash symbols that kind of represent the walls of the maze. And then we're to write a method that we're given like a starting location. And then it recursively calls that method to find a solution out of the maze. And the solution to the maze is when you reach an opening. So if you reach kind of the end here, then you found a solution, and then you're supposed to print it out. And so here, and you print it out with little periods. And so here's one solution that they found, and they marked it with little periods. So let's see. So how does recursive backtracking even work? Do you want to try to give that a shot?
Sure, yeah. Whenever you call a method, that moves the method onto the call stack, and until the method reaches its last line, it is there. So, if you call escape maze and then it calls escape maze and it calls escape maze, as long as the method doesn't reach its last line, all three of those exist, right? And they will exist until they reach that last line. So recursive backtracking takes advantage of that to, after the recursive call, execute everything in the opposite order.
Right on. So I kind of want to show this another figure from our textbook, but again, I'm kind of worried about copyright issues. Okay, so it's chapter 12 in our textbook, and I don't know if I've mentioned it before, but it's called Building Java Programs, and it's by Stuart Regis and Marty Stepp. It's a really great book, highly recommended. Chapter 12, they talk about recursive backtracking. You have kind of a decision tree, and so what you do is you kind of search all branches of this tree until you either find a solution or you don't. And if you do, then you usually say, yay, I found a solution. And then you go back up the branches of the tree until you find a spot where there's a branch that you haven't explored yet. So then you go explore that branch of the tree and see if there's any solutions in that thing. So kind of in a technical way, they'll say there's like a solution space, right? There's a whole set of solutions. And what this recursive backtracking is doing is trying to find all of the solutions in this kind of solution space. I don't know. I feel like that's like kind of, for me anyway, that's like the easiest way to think about it, is this kind of like this tree, and you're just exploring all of these branches. But then how do you put that image in your brain into code? That's another story. And I guess that's kind of always true.
I just thought of an example. Say you have some kind of method. It's telling you to read a book to page 50. And on page 50, it tells you to read the same book till page 50. And then, it keeps on going like that until you run out of books. That's your base case, right? Then you read the rest of the book, throw that one book out, and now you're on that other book, right? Because you have like 10 books lined up and you've read up to 50 pages on all of them. And so now you're going all the way back down, reading the rest of each and every single book until you reach the end, and then you're done.
And then he read all the books.
Yeah.
Right on. Cool. So so we've already talked about kind of recursion and the types of problems that lend themselves to recursion. But I'll just repeat it. It's the idea where you can take a problem and then reduce it to a smaller problem of the same type. And you keep doing this process until you finally reach a problem that's so easy that you just return that answer, so to speak. So in this case, for the maze, the solution, right, is when we reach the edge of the maze. And so if we reach the edge of the maze, then we say, yeah, we found it, and then that gets kind of returned back to all the previous calls until we're done, and we find and we have the solution. Yeah, so this is maybe not the easiest problem to kind of have an introduction to, but I thought we would go ahead and try it anyway. Okay, so there's this maze.java that's provided to us by Code Step by Step, and so I just downloaded that to my computer, and I created a project in IntelliJ called Maze, and I just opened up this file in here, and here's all the stuff. Here's what it looks like. It's a bit, I think it's worthwhile to talk through it a little bit. Like I said, we talked about this a little bit on Tuesday during class, but I'm just talking about it a little bit. So it has a couple of constructors here. And so what these constructors are doing is taking basically a string and then parsing it into a 2D array. So what I did was I created a main method, and to try to implement this, and I wanted to put it in here, but Jasper wants me to make a tester program. He doesn't want to sully our class definition. So I'm going to make another one here, and I'm just going to call this maze tester. And inside of here, I'll go ahead and put a main method. Looks something like this. So basically, the idea is that we're going to call the maze constructor with this string. And so each row is kind of separated by new line characters. And I just realized that my tabbing is pretty awful here, but we can check it out. And so I just recreated the maze that was in the Code Step by Step problem. So that's what that does. It just parses the string into a two-dimensional array, has an equals thing to check to see if two mazes are identical, kind of like with the hash marks and everything. I don't think we really need it, but we do have a get height, a get square, a get width. The is explored is kind of important because once we've explored a spot in the maze, we don't want to explore it again. So we can check to see if something is explored. Oh yeah, I should probably go up to the top here. There's two-dimensional arrays. One's a two-dimensional character array called squares, and that represents the maze. And then there's a two-dimensional Boolean array that just it's true if that spot in the maze has been explored, and it's false otherwise. So you can check to see if a certain spot in the maze has been explored by using this is explored method. You can set explored. So let's say during our backtracking here, or during our traversal, we we're exploring a cell, so we set it to be explored so we don't explore it again. Set square here is basically, you can, so remember on the code step by step, we have to make all of these, we have to set our path to be these little periods. And so that's just the way to set it to a period. So if we find a solution, then on the way back up the decision tree, we set all of those to periods, and then we print it out, is basically the idea. So that's what set square does. ToString just prints the maze out to the console. Check indices is just used internally to make sure that you're not trying to go out of bounds of the maze. Is escaped is not used anywhere. I think with what we're going to do, I have a feeling that it's some internal thing to code step by step. Maybe when they're testing our programs, maybe they use is escaped, but all it does is it just loops around the edges and looks for a period, which means that you escaped. So I don't know what use they're going to use that for, but, and then here we go. Here's our code. Our code goes here. Okay, so what we want to do is write a recursive method named escape maze that uses recursive backtracking to find a pathway out of a two-dimensional maze. I know you all can read, but assume the maze is represented as an object of class maze, which is provided to you. So that's what we've been looking at. A maze object stores its data internally as these two-dimensional arrays. Zero is the row 0 is the top, and column 0 is the left edge. So using the typical kind of Java origin for the axes, right? The upper left-hand corner is the origin. A maze contains walls and empty squares. Empty squares are represented just by a space character, and any other character is considered a wall. So we could make our walls like really pretty, use like some ASCII code or something. I don't know. We can make it pretty, but your method should accept 3 parameters. So we're going to be given a maze, and then a starting position in the maze, and then we are to move up, down, left and right in the maze to try to find an open spot on the outer edge of the maze, right? And so, which would be an exit. So if we can reach that open spot in the maze, then we found a solution, and then I think it tells us to print it. So here's a summary of the methods in the maze.java file. So for example, you might have a maze that looks like this below to the left. And so we're wanting to find a path out of this maze starting at row 6, which is, let's see, so 0, 1, 2, 3, 4, 5, 6 is right here, right? So we're going to start there, and then try to find a way out of it. So here we go, maze. So we're going to call it with this maze, and starting at row 6 and column 1. Then whenever we call our method, it should print out the maze with all these little periods marking kind of this solution. And I hope that's not important. Oh, that's my wife. I got to answer it. Yeah, so we find this path through the maze, and then we print it, so got that phone call. I totally forgot where we were. Anyway, all right. So we're going to try to find a solution to this maze and then print it out, and we do these periods. Okay. I'm going to try this. Okay. So here's like a text editor version of the maze, and let's just try to figure out what's going on here. So we're going to write a method, first of all, called explore, and it's going to explore this maze, and we're going to start at this location. And oh, I remember now what I was going to say. According to the instructions, right, we're to look up, down and then left and then right. That's not hugely important, but if we're trying to match this exact output, then I'm going to stick with this up, down, left, right. Okay, so let's see how that works. So we're going to start at this location. First thing we're going to do is we're going to look up, and then we got to check for the base case, right? What is the base case? Well, we're taking this maze problem and we're trying to reduce it to a smaller problem of the same type. And we keep doing this process until we finally reach a point where the problem is so easy to solve that we can just report that answer. So our base cases are either we've reached the end of the maze, then we just return true, we reach the end of the maze, or we reach a spot where there's just no solution, right? And we return false. And that's going to be like, if we, maybe that's the wrong terminology, but if we reach a wall, right? So if I get to a point, so I'm at some spot in the maze and I look to the right and it's a wall, right? Then I'm going to return false because that's not a solution, right? And so those are going to be our base cases. So we're going to look up, down, left, right in each of these. We're going to do these recursive calls. Okay, so we're first looking up. Okay, it's a blank spot, so we're good. So we're going to set this spot as being explored because now we've been there. So we set that explored. We don't want to go there again, right? So we set that as explored, and then so now we make another call to explore. Well, what does explore do? Well, it makes a call to itself to look up, right? So it looks up again. Well, what does that call to explore do? It calls itself to look up, and it keeps doing this until we reach this point. Now, at this point, we've made a call to explore. It's going to look up. But when it looks up, it turns out that that's a wall. So that call is going to return false to the previous call. And so we go back to, now we're back at this spot. Okay. So now we're back at this. The next recursive call is going to be to look down. Well, we look down. That spot we've already explored. Okay. So that returns false. So now we go back up to this call. Now we're going to look to the left. Well, so we look there. That's a wall. Okay, so that returns false. So finally, we're back at this call, this explore call, and it's down to the fourth recursive call. We're going to look to the right. And so we look to the right and it says, oh yeah, that's great. It's blank. I can look there, right? So we set that one as explored. Do the same process. This call is going to look at up. Nope. It's going to look down. Nope. It's going to look to the left. Nope, because we've already explored that one. And so then it looks to the right. And so now we're here. This call to explore is going to look up. It's going to look down. It's going to look to the left. Remember, we've already explored it. So we don't go there. So we go to the right again. Right. And so this is the process. So first we check our base cases. And if we have a base case, we're either going to return true or false, depending on if it's a wall or if it's an opening, like if we escaped. Otherwise, we make a recursive call to the function itself to look up, down, and left and right. And that's kind of the game plan to do this. So let's see how quickly we can do it. I think there's going to be some details here. It's like I said, it's a pretty complicated problem, I think. And so here is where we are supposed to put our solution. Our code goes here. So first, typically in these backtracking problems, you kind of have the recursive method, but then you have a helper method. Yeah, let's see. I'm just going to go ahead and start writing here. So we're going to make a public, and it's just be static. I'm going to make this one a Boolean. So it's going to return true if it found an escape, or false if not. And we'll call this explore. and we're going to take in a maze. We're going to take in a maze and a row and a column. Like so. All right. So base case. We reached a wall. Right? So then we're going to return false. Another base case is we escaped. Let's do we already explored it. Right? So if we've already explored, then we're going to return false. Okay. And then the best based case, I guess, is that we escaped. And so in that case, we did I spell that right? No, I didn't. In that case, we return true because we found the escape. All right. So once we've done that, now we need to do the recursive calls. And again, because I've been looking at the solution for a long time and I've written it a couple times. First thing we're going to do, so we haven't reached the base case. So now we're going to enter into the recursive case. But the first thing we're going to do is we're going to set this spot as explored. So that way we don't explore it again. Okay, so we'll do that and then we'll do the recursive case. And so what we're going to do is we're going to explore up, down, left, and right. Okay, so this is the plan. This is the plan for our explore method. And so then for our escape maze, which is what the code step-by-step is asking for us, we're going to make a static void method here called escape maze. And this takes a maze and also a starting row and a starting column according to the project and to the problem statement. Okay, and so what this is going to do is, so if we explore this maze and it returns true, right, then that means that we found a solution to it. So this means we found a solution. Whoops. And it doesn't like explore. Why not? Why is it giving me red here?
Because you don't have a return statement, I'm assuming.
Oh, okay. There we go. Found a solution. And so then in this case, we're going to print it out. We'll just print out the maze. And then otherwise, we'll say, we'll just print out that there's no solution, like so. And yeah, okay, so that's going to stay red until, whoa, well, the red went away. I don't know. Anyway, whatevs. Okay, so there we go. Okay, so let's just get the base cases out of the way because I think those are the kind of the easier ones. So we're just going to say, so if we reach the wall, so we can say if maze dot, let's see. So if we reach a wall, so column has to equal so I'm sorry. So I was thinking of using the width and the height, but I think what we want to do is so the wall, right, is anything except for a space. Right. So it's the hash marks in the example. But like I said, we could make it pretty with like ASCII characters and stuff or whatever. So if it's a space, then we're good to go there. But if it's anything but a space, then it's a wall, right? So we're going to say if maze dot, and then we're going to use the get square method for this particular row and column. If it's not equal to a space, then it's got to be a wall. And so then we'll return false, right? So that's not a solution. All right. If maze dot is explored, row column. So I guess if it is explored, then we return false, right? Because we've already explored it. And then finally, we can say, let's see, how do we do this one? So if we're escaped, then the row is either 0, which is the top edge, or it's equal to the height minus 1, which would be the bottom edge. And then the column, if the column is 0, or if it's equal to the width minus 1, then that's an edge. So if any of those conditions are true, then we've reached the edge and we return true. Okay, so I think that's the plan here.
I also think it's worth noting that at this point in the program, it is not a wall.
What do you mean?
Because we passed the base case checking if it's a wall, so we don't need to check if it's a wall here.
Oh, okay, got you. Right. Yeah. Okay, so maze dot, so if we're not equal to that, or column is not equal to, it is equal to 0, or column is equal to maze dot get width, and I just realized I didn't put a -1 on that previous one. If this is true, then we're definitely going to return true. Let's see, so this is get height -1, I believe. Okay, so and also I think if we reach this point, there's another little, there's a lot of details here. All right, but I'm just going to write it down. I think it's easier to write it down now, and then we can talk about how it works later. But we need to mark this little spot. Actually, you know what? Let's not do it. Let's not do it. We can do, we'll try to figure it out later. Okay, so these are our base cases figured out. So now here's maybe a little bit tricky. So we're at some spot in the maze, and so we got to set this thing as explored so that we don't explore it again. And so we're going to take this row and column and set it as true. So we explored this one. Okay, so now I'm going to, in the interest of time, copy paste this code that I have, and then we'll run it. And then I think it'll be more instructive to go through the details of what the code does. I think that'll be more instructive instead of just you watching me type a bunch of stuff, right? I mean, okay, so what we're going to do is we're going to explore up, down, left, right. So here it is. Okay. And I'll go ahead and move this one down to the next line, so it's kind of a little bit easier to see. So what we're going to do is we're going to explore going up. So that's where we take the row -1, and then either that's going to return true, which means that we found an exit to the maze, or it's going to return false if we didn't. And then and then we'll also check going down, right? So row +1, and then we'll check going to the left, and then we'll check going to the right. So column +1. So going to the left is column -1, and going to the right is column +1. Okay. If any of these things are true, if any of those paths that we took returns a true, then what that means is that we found a path through the tree. And so now we're going to set that little square to a dot and then return true. Otherwise, we're going to return false. Okay. I'm going to go ahead and put the little thing up here. Okay, so if we reach the edge of the maze, right, we're going to set that to a little dot. I want to try to see if we can make sense of this, why we're doing this. Okay, so this is the code. So let's step through it and see if we can figure it out. So again, what we're going to do is we're going to start at this square here. So I'm going to call that 0. Okay, this is our first call. So we're going to call wherever where is it right here? Escape maze, right? So explore gets called with start row and start column, which in the example in the code step by step is 6,1, right? So we're going to start at this part. I'm going to call that the 0th call. Okay, so we go in here. Are we at a wall, right? Is it not a space? Nope, in this case it is a space. Okay, that's not good. So that's not a base case. Have we explored it yet? Nope. Is it at the edge of the maze? Nope. Okay, so now we're going to set this little spot as being explored. So it's going to be now that little that two-dimensional array is going to be true. And now we're going to call explore on row -1. So we're going to call explore on this spot, right? So maybe we'll call this call number, we'll call this call number 1 right here. Okay. All right. So now we're calling it on that spot. So we go back up here to the beginning. Now we're calling it with row -1. Is it not a space? Nope. Is it already explored? Nope. Is it the edge? Nope. All right. So we do now another recursive call, but on row -1 again. So now we're going to go up to this next row. So this is going to be our second call, right? And you can see the pattern here. Then it does a recursive call to itself again. This would be the third call. And then we have the fourth call. We keep going up until we get here to the fifth call. So now the fifth call is going to call itself, but again with row -1. So we go back up here and we're calling it, and in the first base case is met. It's not a space. So now it gets returned false. So that fifth call gets what's the word? Returned false. So now we're going to look at the next case, the next explore call. Well, now we're going to look one row down. So we're going to look down, right? So this fifth call is going to take a look at this spot, which is where that 4 is. So we come up and first of all, it is a space, right? Because we haven't written anything there yet. But it is explored, right? Because our set explored on the fourth call set that little spot as true. So it has already been explored. So we return false. Okay. So now we go to, so this one returns false. This call returns false. Now we go to the next call, which we're going to go to the left one. Well, that hits a wall again. So that's going to return false. And then finally, we look to the right with column +1. Okay. So that's going to look right here at this spot, and it's going to call that one. So we'll call that call number 6. Okay. Call number 6 is going to look up. Well, that's a wall. Then it's going to look down. Well, that's a wall. Then it's going to look to the left. Well, that's already been explored. So then it's going to look to the right. It's a blank spot. Way. So we'll call that call number 7. 7 is going to call the function again, up, down, left, and then go to the right. It's a blank spot. Yay. So we're going to call it again, up, down, left, no good. We go 9. Now 9 is going to look up, but that's a wall. So then it looks down, but that's a blank spot. So now we're going to explore that one. So let's call that 0. Okay. And we keep going up. No. Down. Yes. Right. So we look at that one. Up. No. Down. No. Left. Yes. So let's look there. Up. No. Down. Yes. Okay. So we look there. Up. No. Down. Yes. So there we got 4. I'm just going to finish this out. Bear with me. Up. No. But down. Yes. We can look down. Okay. Now here's where it gets a little funner. So now this, I don't know what call this is, the 16th call, right? We're going to look up. That's going to return false. Look down. That returns false. Now we're going to look to the left, right? So that's going to be the 6th and the second 6th call. That looks up, nothing. So it looks down. That's going to be 7. And now we're here. it looks up, that's already been explored. Looks down, that's a wall. Left is a wall. The right is a wall. So all 4 of these calls return false. So that's all done. So the whole thing returns false. So this 7, the 7th call returns false to the 6th call, which returns false to this 5th call. But the 5th call, remember, it called looking up, then it called looking down, then it called looking to the left. That whole branch of the decision tree returned false. So now we're still in that 5th call. It still has to look to the right. So it makes the call and looks to the right. So this now becomes 6. Then up, no. Down, yes. So we go 7. Look up, no. Down, yes. So we call 8. That's the 8th call. Up, no. Down, yes. So we got 9 here. Up, no. Down, yes. I'm going to go back. I'm going to switch back over to 0. Up, no. Down, no. So now we go left. So it's 1, right? And we go left again, and then we go up and then left and then down until we reach this spot. And then that returns false to the previous call, which returns false to that call, which returns false until we get all the way back to here. And looking to the left, right, which is this kind of branch in the tree, in this call, in this decision tree, that returns false. So now we still have to look to the right. So it goes to the right. Oh, I'm sorry. Actually, we go back to the 0. We get all the way back to here. Sorry. And then it looks to the right. So that's 1. Then it goes up. That's 2. And then it goes up, no, down, no, left, no, because we've already explored that. So that becomes 3. And then same kind of reason, we go 4, up, and then we go down in this little spot, this little branch of the tree, but that returns false back to the 4. And so finally we get to the 5. And now we've reached the base case where it's escaped, right? So here we have it's escaped, right? And so what we're going to do is we're going to mark that spot with a little period, right? That little spot gets marked with a period, and then it's going to return true to what the call before that. So we mark this spot number 5 with a period, and then it gets returned true to this call, which was this 4, right? And we found out that one of these was true, right? Because this looking to the right call, this one, right, returns true. And it's since it's all ors, only one of them needs to return true. So that returns true. So now we're going to mark that square, that spot with a period, and then return true to the 3rd call, right? So 4 gets turned into a period and returns true to 3, which gets turned into a period. And all of these calls, it just, this is kind of the recursive part, right? So now we're going back up into the stack of all of these recursive calls and turning these into periods. All right, so all of these are finally getting bam, right? And so that's what this is doing. That's kind of this recursive backtracking. So you go down this decision tree, and if you reach a solution, then you kind of backtrack back to the beginning, and in this case we're writing little periods. Or if you reach a dead end, you go back up in the tree until you find another spot where you haven't explored it yet, right? In that very last case, we didn't explore right yet, so we explore that branch of the tree and try to find it. And then once we find a solution, the whole thing just unstacks, unwinds, however you want to think about it. What do you think?
I think yeah, yeah. So if it does find a way out, it will return true as the very last thing. But if it doesn't, it'll return false. So back in our original escape maze, we can say if explore, that means that we found a solution, right?
Yeah. Yeah. So if explore returns true, then we found a solution, we print it out. Otherwise, we say there's no solution. And by the way, I should be a little bit careful here. I think, well, maybe not. Actually, I'm thinking, because there's more than one solution to this problem. There's more than one solution to this maze, right? I mean, we could have went, I could have went maybe this way. So I'd have to go. So like I could have went here and went all the way to here and then down, right? And then to the right. And that would be a solution as well. And then also notice the way that this is set up. And this is actually the other thing I wanted to do, but I think we're out of time. But it's to find all the solutions. But like down here at the very bottom, because it looks up and then down first before looking left and right, it goes down to this spot. And then up is blocked, and then down is blocked. So it goes all the way down this branch, and then that all returns false, right? So then it looks right. So the solution, it kind of goes down and then up, back up again. But this, if we got rid of those two, right, that's totally a solution as well, right? But that solution doesn't. So if we had looked to the right first instead of looking to the left first, then we would have got that solution. So there is another way to do it, and the textbook is really good, right? But they do this northeast problem. And honestly, I didn't read the Sudoku problem yet, so I'm not exactly sure how they solve that one. But they do this northeast problem, and again, it's this idea of a decision tree, and you find you're finding the solution space. You're finding all of the solutions. So there's a way to do this that way. I don't know, but maybe we can do that next time. I don't know.
Yeah, I think a good thing to look at again is that is explored method. All it's checking is for that period at the end. So if you didn't go exactly in the up, down, left, right way, and you did get an output like the one that's on the text file right now, that's still correct, right? All it's looking for is that you found the end.
I think, I'm not sure. You said is explored, but I think you meant something else, because all is explored
Is escaped, my bad.
Oh, is escaped. Okay, good. Yeah. And I don't even know, where is escape is even, it's not used in this program. But maybe Code Step by Step uses it internally or something. Yeah, I don't know.
One thing in the SI session we did is because it's only checking for that one period at the end. If at the end you change it from the if explore, the recursive call, you can just say return all of that, because it doesn't matter that you set all of those to a period. I mean, you don't see the way that it goes through, but it's a little.
Oh, got you.
Looking.
Yeah, sure. I like to see the periods though.
Yeah, I mean, that's how we did it first.
So yeah, so I did it. I found all the solutions, and it's nice to see the periods, because then you can compare them and you can see how the algorithm, it takes one path and then it takes a different path and then it takes the other path. And I think there was like 6 solutions, something like that, to this particular problem. So it's fun to see the periods, and also you can kind of compare to make sure that your program's doing the right thing. But
yeah, it'd be cool to get like the shortest route out of the maze.
Yeah. So you'd have to keep track of the length of the path, which you could. How would you pass another parameter to the method, like some kind of a counter? Yeah, I hate that. That's one tricky thing about I think recursion. It's either you set a global variable or you add another parameter to your method that keeps track of some kind of thing that you're trying to keep track of. Definitely, I'm not an expert. It's still bonkers to me that this works. It's still bonkers. Yeah, it's because we didn't do anything. It feels like we didn't do anything. Like it's just, we're calling the method itself to tell me true or not. In this base case, right? That's the whole trick to it, is that you come down to a final place where the answer is super easy. Either it's a wall, or you explored it already, or you got a solution, and that's it. It's crazy to think about a problem that way. Yeah. It might be worthwhile to try to think about it like doing it with for loops or something like that. I don't know. So, right, it's kind of interesting. Lots more fun we could have with this, but I think we're gonna, unless you got anything else you want to add, I think we're gonna
No, I
hit
think this
pause.
is great.
Okay, cool. All right. Yeah, I feel like there's some stuff in there we kind of missed, but that's okay. Hopefully it was still fun. So yeah, I guess that's the end of another Building Janky Programs episode.
Like, subscribe.
Like and subscribe. All right, bye y'all. See you on the next one.